molar mass, or the concept of molar mass, is one of those things in physical science that you're like, oh, it's the mass of 1 mole. That's it. It's the mass of 1 mole. 1 mole of anything. And we're going to talk about the molar mass of the elements. So, for instance, right off the bat, see if this works. Yep. See if you recognize my little pile of carbon-12. And we said actually we use carbon-12 to define what a mole is, in a sense. So if you have 12 grams of carbon-12 atoms, then you have 1 mole of carbon-12 atoms. So then, in other words, the molar mass for that particular form of carbon-12, that molar mass is 12 grams per 1 mole of carbon-12 atoms. So that's the molar mass. It is the mass of 1 mole. Get it? Molar mass. I like it. So we're all about units in here. And so the units of molar mass are going to be grams per mole, or grams per 1 mole. And so there are just kind of like density, the units for density. I don't know if this works for you, but units of density are mass per volume. So for instance, grams per milliliter. Okay, that's how it's written, but you need to unpack that to use it as a conversion factor in grams over 1 milliliter. So that's kind of why you need to be able to kind of take grams per mole and unpack it. Grams in the numerator or top, moles in the denominator or bottom. One more kind of way we might represent that is anything that's in the denominator can be raised to the power it is, which in this case it's the first power, but minus to negative first power. So that's just for your information. So here we have sulfur and carbon. So this isn't actually carbon-12 over here. This is just regular carbon in nature. It has a couple of different isotopic forms. So its molar mass is 12.01 grams per 1 mole. Sulfur, it's 32.07 grams per 1 mole. So the different elements have different molar masses. So here is, and it's not really necessarily a trick, I'm going to kind of show you a proof why this is. But remember, we've been talking about the periodic table. This is my periodic table element, and I'm going to pick on this element. Of course, that's carbon. And you're going to see for carbon, it is atomic number 6. So you'll see the whole number in there. And then you'll also see a decimal number for carbon. So of course, 6 is the number of what? The number of protons. It's the atomic number. So you'll see a decimal number, and the decimal number for carbon is 12.01. And we actually talked about how that decimal number for carbon means that actually if you come up with a weighted average of how much a carbon atom weighs, it weighs 12.01 AMUs. Now, I'm here to tell you that not only do we use the decimal number for the average atomic weight, but we also use the decimal number for the grams for 1 mole of that element. So not only can we use that decimal number for carbon like that, but if you have 1 mole of, now this isn't carbon-12, but just kind of in nature how carbon appears, if you have 1 mole of carbon, then it is going to weigh 12.01 grams. Okay, that is the molar mass of carbon, and that's the decimal number. So I hope you're okay with that. That's kind of, and I'm going to show you proof why that is. So it's how much it weighs, and it's also its molar mass. So I went ahead and brought this slide back in again. I don't think you guys have it again, but we said that there's 1 mole of atoms, sulfur atoms here, magnesium atoms here, tin atoms here, silicon atoms here, and copper atoms here. So what I've done is grabbed a periodic table, and I'm going to tell you then, for sulfur, for instance, I looked it up, and the decimal number is 32.06. 32.06. So that is the molar mass. That's the grams of sulfur per 1 mole of sulfur atoms. Does that make sense? Okay, magnesium, it has a decimal number of 24 24.31. Okay, so for magnesium, the molar mass is 24.31 grams per 1 mole. 1 mole of magnesium atoms. The decimal number for tin is wow, it's pretty heavy. 118.71. And notice in all of these cases, I'm going with 2 decimals, and we'll talk about why that is. But that kind of works well for working chemistry problems. Molar mass then are units of grams of tin per 1 mole of tin, right? And then we go on to silicon. The molar mass, or the decimal number for silicon, is 28.09. Again, a silicon atom on average would weigh 28.09 AMUs. And scaling that up, if you want 1 mole of silicon atoms, you would set aside 28.09 grams. So the molar mass for the elements is going to depend on what the elements is, and you get it off the periodic table. It's that decimal number we've been talking about earlier. For copper, the decimal number is 63.55, so that's not only its average atomic weight, that's also its grams to get 1 mole of copper atoms. Very good. So this is my proof to kind of show you why the atomic weight, the average atomic weight, also does double duty. That decimal number does double duty for the molar mass. If we pick on copper, and the decimal number for copper is 63.55, that means there are 63.55 AMUs in general is how much one atom weighs. We go ahead and introduce the equivalency statement between grams and AMUs. We talked about this before. A gram is really big and AMU is really small. So I'm thinking this is, I think there's uncertainty here, 4 sig figs. But anyway, 1 gram is equal to 6.022 times 10 to the 23rd AMUs. We're going to do this so the AMUs cancel and we have grams per atom. All right, and we're actually going to go for grams per mole. So we need to go ahead and do a third term. And this third term is going to go ahead and get moles, go ahead and let atoms cancel, be left with units of moles in the bottom. We've been talking about 1 mole is equal to 6.022 times 10 to the 23rd atoms. So setting up this way, like I said, AMUs cancel and atoms cancel. We're left with units of grams per mole, which is great. And honestly, it seems like magic, but it's not really. Notice that these terms, Avogadro's number cancels. So we literally end up with, for copper, that same number, decimal number 63.55, but now units are grams per mole. So that's just kind of a proof. We could have done that for any element, but I just kind of showed you why that decimal number does double duty.